Hi everyone, we're doing lesson 4 in relations and functions. So lesson 4 is talking about functions. So we're looking here on our screen. We're studying the following relations. They're categorized by functions and non-functions. So let's look at the functions. We want to say what is similar about the non-functions. So if I look at my functions, I've got 2, 3, 4, -1, 6, 3, 8, -1. Here, for my x values, I have 1, 2, 3, 4, 5. And my y values 2, 4, 6, 8, 10. In this graph, I've got my x values across the bottom, my y values going up and down. So I get this nice straight line graph here. I have, again, my x values across the bottom, y values up and down, and similar here. So just taking a look here, what I notice is that I have x values and y values. I have a little bit of repetition in the y values, but not in my x values. I only have one value for x across the board. Here I have, if I look at my value for x here or here, I only have one possible y value. However, I do have repetition in my y values. Similar thing happens here. So that's what I notice about my functions. My non-functions, however, what I can notice is that I might have repetition in my x values. Notice that there and there, that I have two different possible values for the x value 1, two different possible values for the x value of 12. Here, for my x value of -2, I have two possible y values, similar here and here, and here and here. So when I look at them, how are they similar? Well, they're still pairs of values. So we still have pairs of values. How are they different? Here I have only one y value for each x. The same cannot be said. That's for the functions. Okay, same can't be said for the non-functions. The non-functions, I might have more than one possible value. Okay, so let's continue on. So this draws us to our conclusion. What is a function? Well, a function is a special type of relation. So it's still a relation, but it's a very specific type of relation where each element in the independent variable, the domain, usually x, is associated with exactly one element in the dependent variable, usually y. So every input has only one output. And again, usually y. Sometimes we do have different values as opposed to x and y, but usually x and y. So now we want to look, and we want to look at some relations. We want to determine, are they functions or not? So for each relation, we want to, first of all, determine whether the relation is a function, and then identify the domain and range of each relation that is a function. So let's look here. A relation that associates given shapes with the number of right angles in the shape. Right triangles have 1, acute triangles have 0, squares have 4, rectangles 4, regular hexagons have 0. So for each input, I only have one option. If we're taking the shape as the input, sorry, I'm going to erase that and make that prettier. I'm really going to do it this time. So if the input is the shape, the output is the number of right angles, okay? And I only have one relationship for each shape. That number doesn't change. So we would say that number 1 is a function. So if I'm then doing, if it is a function, I have to do 2, which is telling me the domain and range. Well, the domain would be my input, which is the shapes. So I have my right triangle, my acute triangle, I have my square, I have my rectangle, and I have my hexagon. Okay, my range would be the number of right angles. So I have as options, I either have 0, 1, or 4, and no 2s, no 3s. Okay, now looking at this next one, we have for these numbers, these are the squares of those numbers. So looking at this, if I have 1 and I square it, or it is the square of these numbers, sorry. So -1 times -1 gives me 1. 1 times 1 gives me 1. Now remember, this is our input, and this is our output. -3 squared gives me 9. -2 squared gives me 4, but +2 also gives me 4. So if we look at that, we know that this is not a function because inputs 1 and 4 each have 2 outputs. Now, interestingly enough, if it had been written the other way, it would actually work. But it's written in the form that this is the input and this is the output. So when it's written in that expression, we would say it's not a function. Now, how can we test? Well, one of the ways we can test is if we graph the data, we can do what's called a vertical line test. So a graph represents a function when no 2 points on the graph lie on the same vertical line. So what we do for this is if we have a graph of a function or a graph of any relation, and we place a pencil vertically on the graph, then slide the pencil up and down across the graph. So here, I put my vertical line here. I could also put my vertical line there or there. If that vertical line only intersects at one point, the graph represents a function. So this one would be a function. When the domain is restricted to a set of discrete values, the points on the graph are not connected. Okay? If I look at this non-function here, when I draw the straight line like so, I have 2 points where it crosses. And the same thing happens here and here. There are a couple places where it only touches once, but if there's any place where that vertical line crosses twice, it is not a function. Okay? So because this one crosses twice, not a function. Okay? And this one, no matter where I draw that vertical line, this one is a function. Okay? Yay. All right, so let's keep going. So let's test. We're going to look at these and we're going to determine whether each relation is a function or not a function and give reasons for our answers. So looking at this first graph A, if I draw a vertical line, I can draw it here, crosses once. I can draw it here, crosses once. Sorry, my vertical lines are not so pretty. I would say that this one is a function using the vertical line test, okay? Every input only has one output. For B, if I draw a vertical line here, crosses twice, here, crosses twice, so this is not a function. Okay, using the vertical line test, crosses twice. Okay, and so for some inputs have two outputs. Okay, looking at C, if I draw my vertical line here, I have way more than one option. So this is not a function. Okay, and remember, it's just a vertical line. Horizontal lines don't matter. This is called the vertical line test. So more than one output per input. Okay, let's keep going, do some more. D is we can't use the vertical line test, but we can take a look at what's going on. This is a table. Well, if I notice here, I have X as 1 and X as 1, and I have two different inputs. So this is not a function. Input 1 has two outputs. Okay, so it can't work. All right. Next one, I have 2, 3, 4, -1, 6, 3, 8, -1. So I have only one option for each of my X value. So this would be a function. For each input, there's only one output. Okay. Next one, F. I can use my vertical line test. If I draw a vertical line here, crosses twice. So this is not a function. Okay. So it fails the VLT. Okay. All righty. Identifying whether a graph represents a function. So based on these, we can take a look and we can think about what we've learned. I'm going to change my color to the green because it'll be easier to see. Which of these graphs represents a function? Well, if I look at graph A and I draw a line through here, I can notice that it crosses more than once. Similarly here, so I would say that this one is not a function. With graph B, or the second graph, world population, there is no place where I'm going to cross it twice. I'm only going to cross my vertical line once. So this is a function. And I might write that in a darker color just because the green I know doesn't show up as well. So this one is not, and this one is. Hopefully we're getting the pattern, particularly with a graph. It's probably easiest to see a function with a graph as opposed to with a table. With a table, you really got to read the data to kind of figure it out. Okay. So let's keep going. Now we also want to use something called function notation, and it's a way we can write our equations. We're used to seeing our input as X and our output as Y. Now we give our equations special names like F and G. And these names will help us distinguish between different equations and allow us to see input values more clearly. So if I wanted to express a function and then I just want to change the input, I can write it as such. So f of x is equal to 10x minus 8. So what I'm saying is for every place that I have x, I'm inserting the value of 2. And this will give me my output, or my y. So I would just substitute this in. So I want to know what f of 2 is. So I'm looking for f of 2. Well, it's 10 times 2 minus 8. Anywhere I had an x, I'm going to substitute in the 2. So I would get 20 minus 8, which is equal to 12. So f of 2 equals 12. So if I were graphing that, that would be an ordered pair of 2, 12. My y value would be 12. I can do this for a variety of different values. Remember that this, what we're substituting in, is the same as f of x. So anywhere I see an x, I'm going to substitute in that number. So here I take the formula that we've been given, and that's what I am talking about. That's the function I'm talking about. So f of negative 3 is equal to 10 times negative 3 minus x. All I'm doing is substituting in that negative 3 where there was an x. So this would be negative 30 minus 8, which would be equal to minus 38. So f of negative 3 equals negative 38. And again, I can write that as an ordered pair, negative 3, negative 38. Okay? Now we can take a look at thinking about how to solve equations, and we've done this before. If I know f of x equals 42, what I can do is use that value to rearrange and solve for what is the input. So I want to know what is the input. What is x? Okay, so I take my f of x, which is 10x minus 8, is equal to 42, and I'm going to rearrange and solve for x. So 10x is equal to 42. I've got minus 8 on this side, so when I move it to the other side, I'm going to add 8. So I get 10x equals 50. And then I'm going to divide 10 out of both sides to get x by itself. When I do that, I get x is equal to 5. Okay? And the one thing to say for all of these, I always like it if you put a little box around the answer. Makes it easy to find things. Now, oops, I jumped a whole bunch of pages, didn't I? Let's get back here. So if we're doing an ordered pair here, I now know that my x value is 5 and my output is 42. I was given that. Okay, let's do a few more of these. Now, h of x, we've now noted it as h of x because we're talking about a different function. So instead of using f of x, I've changed it and called it h of x. So it's just a way to express it differently, particularly if you're talking about a whole bunch of different functions. If they're all called f of x, it can get confusing. And if you're using them together, so you can call it g of x, f of x, h of x, etc. Just be very clear about which one you're using in which questions. Okay, so looking at this, we're going to do the same thing. So we want to figure out what h of 5 is. So we have a different expression here. Negative 2 times 5, I substitute in 5 for the x, plus 10. So h of 5 is equal to negative 10 plus 10. So h of 5 equals 0. And that would be our answer. Now again, you can write this as an ordered pair. X was 5. My output is 0. And in this case, if we were graphing it, we'd probably call it y. Can do the same thing here. H of negative 3. So negative 2 times negative 3 plus 10. All I'm doing is substituting into our original equation the value of negative 3. Okay, h of negative 3 equals negative 2 times negative 3 is positive 6 plus 10. So h of negative 3 is equal to 16. So my answer, if I was looking at an ordered pair, would be negative 3, 16. And here, like the last example, we're going to solve for our value for x. So what we mean is that h of x, which is negative 2x plus 10, is equal to 6. So I want to rearrange and find out what value of x did I substitute in to get that. So I have negative 2x is equal to, moving this 10x to the other side, I'm going to subtract it, because I'm subtracting it from both sides. So negative 2x is equal to negative 4. And then we will divide both sides by negative 2. And when we do that, I get x is equal to, oh, sorry, I left out a negative sign. So when I do that, I get x is equal to 2. Okay, and my ordered pair here, x is 2, and my output is 6. Okay, now we're going to do a little more practice with functions. Sometimes you can use two functions and you can find expressions for them and evaluate. Okay, so let's see what happens here. So we're substituting in, and actually for this A and B, it'd be a good point for you to try them both on your own. So press pause in a moment, and then when you've done them, press play and see if you got them right. Okay, and we're back. So f of -2, so that means that x is -2. So we're going to substitute this in. We're using f of x. So f of -2 is equal to 3 times -2 minus 6, which is -6 minus 6, or -12. So f of -2 equals -12. Again, if I wanted to write this as an ordered pair, I could write it as -2, -12. Then I can do g of 3. Now we're using a different function. It's a different function. It's g of x. So we have to make sure we're using the right one. So for here, x equals 3. So, oops, look, Mrs. Finley made a mistake. So let's see what happens. G of 3 equals 3 squared minus 3. So let's do this. 2 times 3 squared is 9 minus 3. So g of 3 is equal to 18 minus 3. G of 3 is equal to 15. Okay? And if we wanted to write that as an ordered pair, we could write it as 3 comma 15. Now this next one means we have to figure out the values for g of 2 and f of 2, and then we have to add them together. So we're going to figure out the values for each of them and then add them together. Okay, so g of 2 is equal to 2 times 2 squared minus 3. 2 squared is 4 times 2 is 8, so 8 minus 3, which is equal to 5. So that's my value for g of 2. I'll do the f of 2 in a different color so it's easier to see. F of 2, I go back to my f of x expression, is 3 times 2 minus 6, which is 6 minus 6, which is 0. So I have my f of 2 and my g of 2. If I want to add them together, we'll go back to blue. So g of 2 plus f of 2 is equal to 5 plus 0, which is equal to 5. And that would be my solution. It's probably best to figure each out separately and then add them together. Okay? So we can do that also with multiplying. So let's take a look at this next one. F of -3 and g of -2. So I'm going to just scroll it down a little better so I can see the functions. So let's do f of -3, which is equal to 3 of -3, 3 times -3 minus 6, which is -9 minus 6. And when we calculate that out, we get -15. I'm going to change color for the g of x just for clarity. So g of -2 is equal to, we're using this expression here. So it's 2 times -2 squared minus 3. So g of -2, -2 squared is 4. 4 times 2 is 8. 8 minus 3 is 5. And what I want to know for my final answer is f of -3 times g of -2. So that's -15. Oops. -15 times -2, which is equal to, oh, wait, times 5. Oh, my goodness, people. Making mistakes. This would be times 5. So I would get -75, and that would be my answer. Okay, a little more work with those ones. You have 2 substitutions into the formula, and then you can do the multiplication. Okay, that next one, this one feels easy now because it's just solving for a value for x. So again, we have our expression 3x minus 6 is equal to 54. And I'm rearranging and solving for x. So 3x is equal to 54 plus 6. I move this minus 6 over by doing the opposite operation on the other side. So 3x is equal to 60. I'm going to divide both sides by 3. And then I get x is equal to 20. How about you guys try this next one? Try F. So press pause, and when you're done, come back, see if you got it right. All right, so we have f of x is equal to negative 6. So we have 3x minus 6 equals negative 6. So 3x is equal to, when I move this negative 6 over, it becomes negative 6 plus 6, so it equals 0. Well, x has to be equal to 0 then, because to get a 0 answer, the only thing I can multiply 3 by to get 0 is 0. Okay, so that's a lot of practice with those function notation. Good practice, a lot of different variation. Hopefully that's enough to give you good practice for the assignment. But we do have one more page before then. So on this next one, it says determine the missing values given using the given graph. So it wants f of 2. So using the graph, f of 2, so we look where x equals 2. So x equals 2 and the y value is 1. For the next one, and I'll change my color just to show you. So this means x equals negative 4. So if we go over here where negative 4 is, and we look down, my output would be negative 2. We'll go back, we'll use black this time. So here it says f of x equals 0. So that means I want to know what my x is. My y value, my output, equals 0. So at 0, what is my value for x? So x equals 0. Okay, and similarly here, we'll go back to blue. I have f of, actually, I'll find a custom color. I'll use this purple. My output, Mrs. Finley can't write. My output equals 2. So I want to know what my x equals. So looking here, if my output is 2, so that's up here, that means I'm over here. So my x equals 4. So it's just using the graph to help you find and really kind of clarifying for yourself whether you've been given the input or the output, whether you've been given the x value or the y value. Okay. Now our last example here, the equation C is equal to 25n plus 1,000. So we're dealing with, I'm going to, represents the cost, C dollars, for a feast following an Arctic sports competition where n is the number of people attending. So it says describe the function and write the equation in function notation. So to describe this function, we're going to say that the cost of the event is a function of time. It will cost $25 per person plus $1,000 in other fees. Plus, okay, so it will cost $25 per person plus $1,000 in other fees. So C of n, and I am going to actually change this. I don't think it's a function of time. It's a function of numbers I don't know what that means. Of attendees. Okay. C of n is equal to then 25n plus 1,000. So 1,000 is your base cost, and for every person attending, there's $25. It says determine the value of C100. Okay. So, and it says, what does this number represent? Well, if n is the number of people, then C100 is the cost when 100 people attend. Okay, so let's figure it out. C100 is equal to 25 times 100 plus 1,000. So that's 2,500 plus 1,000, or 3,500. Okay, so we will say it will cost 35. Getting squiggly. It will cost 3,500 for 100 people to attend. Okay. All right. Now it says determine the value of n when C of n equals 5,000. So what does that represent? So let's figure it out first. So 5,000 will equal, we got to put in our function. So it will equal 25n plus 1,000. So let's rearrange and solve for n. So we're going to subtract 1,000 from both sides to get the n's by themselves. Then we're going to divide both sides by 25. And we get n is equal to 160. Okay, so what that tells us is the 5,000 is what it cost if 160 people attend. Okay, so it's important with these functions. Sometimes they reflect real world things, that they tell us that they are telling us something. You know, sometimes they're just numbers on a graph, x and y values, and we're being more theoretical. But sometimes, like this example, they are referring to a specific situation. And a lot of times you would when you're, you know, if you're getting married and you book a hall, you have a deposit, and then you have an additional count based on how many people are attending, because you're going to serve them a meal. So sometimes they do reflect a real world situation. So it's important for us to think these aren't just always just numbers, that the numbers mean something. Okay, and a lot of times that's what we're learning about. We're learning about this so we can express them because of what they mean. Now, what's our assignment? Our assignment from your book, page 311, 1 and 2, 4, 5 and 6, 8, and then challenge 12A and 15. And when you've completed that, then you can do the Google assessment form. Thanks, guys. Okay.